What if I told you that the very fabric of our universe might have been stitched together by something as bizarre as a quantum magic trick? Picture this: the moment of creation, when everything we know was smaller than a single atom, and yet somehow it broke free from nothingness. This isn't science fiction. It's one of the most jaw-dropping ideas in modern physics: quantum tunneling, a phenomenon so strange it feels like the universe cheated its own rules to exist. And here's the wild part: scientists believe this quantum sleight of hand might have been the spark that ignited the cosmos itself. Think about the odds. Normally, particles can't just vanish and reappear somewhere else unless they're playing by quantum rules where the impossible becomes routine. In those first fleeting instants, the universe could have been a cosmic escape artist, tunneling its way into existence from absolute nothingness. It's like rolling a boulder up a mountain only for it to suddenly teleport to the other side. How? Why? That's where things get even more fascinating. Researchers have spun not one, not 10, but 30 mind-bending theories about how quantum tunneling might have shaped the birth of everything from the tiniest particles to the vast cosmic web we see today. This isn't just about equations on a chalkboard. It's about rewriting the story of our origins. Imagine peering into the deepest secrets of reality, where time and space blur, and the laws of physics as we know them flicker like a candle in the wind. Some of these theories suggest parallel universes budding off like branches of a tree. Others propose that the universe didn't just tunnel once, it could have happened over and over, a cosmic heartbeat echoing through the void. And the most thrilling part, we're on the verge of uncovering clues that could confirm which of these wild ideas might actually be true. So buckle up, because we're about to dive into the rabbit hole of quantum tunneling and explore the 30 most incredible theories that could explain how our universe pulled off the greatest escape act of all time. Let's start with the first and perhaps most startling theory, that our universe might owe its existence to a random quantum hiccup. Imagine a void so empty, so utterly absent of anything, that even the concept of nothingness feels inadequate. Yet in this void, particles flicker in and out of existence like static on an old television screen. These aren't just tiny blips, they're quantum fluctuations, brief violations of the rules where energy appears and vanishes in a cosmic game of hide and seek. And according to this theory, one of these fluctuations didn't just vanish. It tunneled through an impossible barrier, sparking the Big Bang itself. Think of it like a ball rolling up a hill without any push. It defies logic. But in the quantum world, particles do this all the time, borrowing energy from nowhere to leap past obstacles they shouldn't overcome. Apply that to the birth of the cosmos, and suddenly, the universe's explosive beginning seems less like a singular event and more like a lucky quantum roll of the dice. Stephen Hawking and others played with this idea, suggesting that the vacuum of space isn't truly empty, it's a seething foam of potential, where universes could bubble up like boiling water. And ours, just one bubble that happened to survive. What's even wilder is how this connects the impossibly small to the unimaginably large. Quantum mechanics, which usually governs particles smaller than atoms, somehow set the stage for galaxies and black holes. It's like a single domino knocking over an infinite chain, except that first domino appeared out of thin air. If this theory holds, it means everything, every star, every planet, even us, exists because of a quantum glitch that somehow stuck around. The universe didn't need a creator or a cause, it just needed a lucky break in the rules. But here's the real kicker: if quantum fluctuations could birth our universe, why not others? This idea opens the door to a multiverse where countless universes pop in and out of existence, each with its own laws of physics. Most might collapse instantly, but a rare few, like ours, stumble into stability. It's a humbling thought. We might be living in the cosmic equivalent of a lottery winner, the one in a trillion universe that hit the jackpot. So next time you gaze at the night sky, remember you might be looking at the aftermath of the universe's luckiest quantum gamble. Now let's dive into something even more mind-bending. What if our universe isn't the original, but just a cosmic downgrade? That's the essence of the false vacuum hypothesis, a theory that suggests reality as we know it might be the result of a quantum energy drop so colossal, it rewrote the rules of existence itself. Picture the early universe not as empty nothingness, but as a high-energy state simmering with unstable potential, like water superheated past its boiling point but not yet bursting into steam. Then, in a single quantum leap, it tunneled into a lower, more stable energy level, and in that instant, the energy released could have ignited the Big Bang. This idea ties directly into Alan Gough's groundbreaking work on cosmic inflation, that split second when the universe expanded faster than light itself. Think of it like a bubble forming in a pot of boiling water, except instead of steam, this bubble contained an entire cosmos. The false vacuum theory takes this further, suggesting inflation wasn't just a phase, it was the universe settling into its true energy state after tunneling through an impossible barrier. And the implications are staggering. If this happened once, it could happen again. Somewhere in the cosmos, or even in our own future, another quantum tunneling event could rewrite physics entirely, erasing galaxies in an instant. Here's where it gets eerie. If the false vacuum hypothesis is correct, our universe might be sitting in a precarious state, like a marble balanced at the top of a hill. Right now, it's stable, but all it would take is one microscopic nudge for everything to roll into oblivion. Scientists call this a vacuum decay, and while it sounds like science fiction, the math checks out. A single quantum event could trigger a wave of annihilation, rewriting the laws of physics at light speed and leaving no warning. But don't panic just yet. This same instability might also explain why our universe has the exact right conditions for life. When the false vacuum collapsed, the energy released could have fine-tuned the cosmos, setting the stage for stars, planets, and eventually us. It's as if the universe won the lottery twice, first by tunneling into existence, then by landing in a state where complexity could flourish. So next time you hear about the mysteries of dark energy or the fate of the cosmos, remember, we might be living on borrowed time in a universe that's still figuring itself out. What if our universe is just one bubble in an infinite cosmic froth, each with its own unique set of physical laws? This is the heart of the bubble universe multiverse theory, where quantum tunneling doesn't just explain our existence, it suggests we're surrounded by countless other universes, each born from their own quantum leap. Picture a bubbling cauldron of space-time, where every pop creates a new cosmos with its own version of reality. Some might have gravity 10 times stronger, light that moves slower, or even dimensions we can't begin to fathom. And according to Leonard Suskind's string theory landscape, this isn't just speculation, it's a mathematical inevitability. String theory proposes that the fabric of reality isn't just made of particles but tiny, vibrating strings. These strings can settle into different energy states, like a piano hitting infinite notes, and each note represents a unique universe with its own physics. Quantum tunneling acts as the composer, pushing these strings from one note to another, creating a cascade of bubble universes. Imagine blowing soap bubbles on a windy day. Some float gently, others pop instantly, but a few drift into stability. That's our universe, one lucky bubble in a storm of possibilities. The implications are staggering. If this theory is true, the constants we take for granted, the speed of light, the strength of gravity, aren't universal rules at all. They're just the local bylaws of our cosmic neighborhood. Elsewhere, universes might exist where atoms never form or where time runs backward. It's a humbling thought. We're not the center of creation, but a single page in an endless library of realities. And here's the twist, these bubble universes might not stay separate forever. Some theories suggest they could collide, sending shockwaves through space-time. Evidence might even exist in the cosmic microwave background, the afterglow of the Big Bang, where strange patterns could be scars from ancient collisions with other universes. It's like finding fingerprints on a window, hinting at worlds just beyond our reach. So why does this matter? Because if the bubble multiverse is real, it answers one of physics' biggest mysteries: why our universe seems fine-tuned for life. There's no miracle, just statistics. With infinite universes, some are bound to have the right conditions, and we happen to live in one of them. It's not destiny, it's probability on a cosmic scale. And that might be the most astonishing revelation of all, that our existence isn't special, just inevitable in a sea of endless possibilities. Alexander Vilenkin's idea is so radical it might make your brain itch. What if the universe didn't come from something, but from nothing? And not just empty space, not even a void with quantum fluctuations, pure, absolute nothingness. No time, no space, no particles, just a perfect blank slate. Then, in a single quantum leap, our entire cosmos tunneled into being. It sounds like magic, but the math behind it is shockingly elegant, and it sidesteps one of cosmology's biggest headaches, the singularity. Think about the Big Bang Theory's lingering problem. If you rewind time far enough, everything condenses into an infinitely dense, infinitely hot point where the laws of physics break down. Singularities are where science throws up its hands and says, "We don't know." But Vilenkin's proposal offers a way out. Quantum tunneling doesn't need a starting point. It's like a cosmic Houdini act where the universe escapes the chains of causality itself, appearing without a prior cause. Here's how it might work. In quantum mechanics, particles can spontaneously appear if the energy balance works out. Virtual particles blink in and out of existence all the time. Vilenkin applied this to the entire universe, suggesting that if you treat nothingness as a quantum state, it could tunnel into somethingness without violating any physical laws. The key: negative gravitational energy. As matter and energy emerged, gravity's pull created a perfect balance sheet: positive energy in stars and galaxies, offset by the negative energy of their gravitational fields. Net total zero. The universe, in a sense, is the ultimate free lunch. This idea flips creation myths on their head. No deities, no primal atoms, just a quantum fluctuation so vast it birthed reality. But how do you even model nothingness? Vilenkin's equations treat it as a point of zero radius, a state where time and space haven't yet uncurled into existence. Then, through tunneling, that point blossoms into a universe. It's like a seedless fruit growing without a tree. Critics argue this pushes quantum mechanics beyond its known limits. After all, we've only observed tunneling in existing systems, not for entire universes. But supporters counter that the same laws governing electrons should, in principle, apply to the cosmos. If particles can ignore classical physics, why not space-time itself? The wildest implication: if our universe tunneled from nothing, it might not be alone. The same quantum process could have created countless others, each with random physical constants. Some might collapse instantly, while others, like ours, stumble into stability. It's a dizzying thought. We're here because randomness rolled cosmic dice and our number came up. So the next time someone asks, why is there something rather than nothing, you can tell them it might just be quantum luck. Stephen Hawking and James Hartle once proposed something so counterintuitive it bends the fabric of reality itself: a universe with no beginning at all. Forget the Big Bang's fiery singularity or a quantum leap from nothingness. Their no-boundary idea suggests the cosmos didn't start in the way we think of beginnings. Instead, it just was, like a globe with no edge, a seamless, self-contained reality where the concept of before loses all meaning. To grasp this, you've got to wrestle with Hawking's favorite trick: imaginary time. Not make-believe, but a mathematical sleight of hand where time behaves like space. Picture Earth's North Pole. There's no point north of it, directions just loop. Now apply that to space-time. At the universe's origin, real time, the ticking clock kind, blends into imaginary time, curling into a smooth, finite surface with no sharp edges. No explosion, no boundary, just a gentle warp where conditions naturally give rise to reality. It's as if the universe tunneled into existence by sidestepping the need for a starting line altogether. The magic lies in quantum gravity's fuzzy rules. In the no-boundary proposal, the early universe wasn't a pinprick of infinite density, but a tiny, four-dimensional space where time and distance blur. Hawking likened it to a shuttlecock. Near the rounded end, the bottom of space-time quantum effects dominate, and particles flicker in probabilities. As the universe expanded, these probabilities crystallized into the laws we know today. The Big Bang, just our human insistence on marking a zero point where none exists. Critics pounce on this. How can time just not exist at some point? But supporters argue it's no weirder than black holes warping space. After all, if gravity bends light, why can't it bend time into a loop? The proposal also tackles inflation elegantly. Without a singularity, the universe's rapid expansion isn't an abrupt kick but a natural unfurling, like steam smoothing wrinkles from fabric. Here's where it gets poetic. If the no-boundary idea holds, asking what came before the Big Bang is like asking what's south of the South Pole. The question dissolves. Our universe might just be one phase in an eternal cycle, where time isn't a line but a mosaic. And that changes everything, because if boundaries are illusions, then maybe so are the limits of what reality can become. Imagine the universe not with a bang, but with a bounce, like a cosmic rubber band stretched to its limit, then snapping back with enough energy to birth an entirely new reality. That's the heart of loop quantum gravity's wildest idea. Our Big Bang wasn't a beginning, but a rebirth. According to this theory, a previous universe collapsed under its own gravity, not into a singularity of infinite density, but into a quantum soup where space and time shattered into fragments. Then, in a defiant act of quantum tunneling, it rebounded, exploding outward as the universe we know today. This isn't just poetic imagery. Loop quantum gravity, a rival to string theory, suggests space-time isn't smooth and continuous but woven from tiny, indivisible loops. Think of it as the universe's fabric being made of threads a billion times smaller than an atom. When gravity runs the show, these loops can't be squeezed infinitely. Instead, they resist, creating a repulsive force so powerful it halts collapse and triggers a bounce. Picture a collapsing star, but instead of forming a black hole, it hits a quantum wall and springs back like a trampoline. The implications rewrite cosmic history. No longer do we hit a dead end at the Big Bang singularity, a point where physics breaks down. Instead, the prior universe's death becomes the cradle for our own. It's a twist on the Phoenix myth, where the ashes of one cosmos fuel the fire of the next. And here's the kicker. If this happened once, it could happen endlessly, with universes cycling through collapses and rebounds across eternity. How does quantum tunneling fit in? During the bounce, the universe wouldn't just crunch and expand classically. It would navigate a quantum phase where probabilities reign, a chaotic realm where tunneling allows the transition from contraction to expansion, skipping the singularity entirely. Think of it as the universe taking a secret detour around a roadblock, emerging on the other side reborn. Critics argue this leans heavily on untested math, but supporters point to subtle clues. If a prior universe existed, its gravitational waves might still echo in our cosmos, hidden in the cosmic microwave background. Others speculate that black holes in our universe could someday become the seeds of new bounces, each one a potential tunnel to another reality. The beauty of this theory, it solves two puzzles at once. It banishes the singularity's paradox, and it suggests the universe might be immortal, cycling through lifetimes we're only beginning to imagine. So the next time you hear about the Big Bang, remember, it might not have been the beginning, just the latest chapter in a story with no end. Roger Penrose's vision of the cosmos is both beautiful and haunting, a universe that doesn't end with a whimper or a bang, but with a quiet quantum reset, like a phoenix reborn from its own ashes. His conformal cyclic cosmology theory dares to suggest that our universe isn't the first and won't be the last, but part of an endless chain of cosmic eons, each one stretching across trillions of years before dissolving into a timeless void, only to tunnel into a brand new beginning. At the heart of this idea is a profound symmetry. As the universe expands, galaxies fade, black holes evaporate, and even protons decay, leaving behind a sea of featureless radiation. But here's the twist. In this ultra-far future, the distinction between a universe packed with matter and one filled only with light begins to blur. Distances lose meaning when everything is uniformly stretched thin. Time, too, becomes irrelevant when no clocks remain to tick. Penrose saw this barren state not as an end, but as a blank slate, a conformal boundary where the dying universe mirrors the smooth, empty conditions of the Big Bang itself. Quantum tunneling bridges the gap. In the final moments of an eon, the remnants of our universe could undergo a radical transformation, tunneling through a quantum phase where the laws of physics momentarily unravel. Just as particles teleport past barriers they shouldn't overcome, the entire cosmos could leap into a new eon, reborn with fresh physical constants and particles, yet still carrying faint echoes of its past. The evidence: Penrose points to strange, circular patterns in the cosmic microwave background, possible imprints of collisions with black holes from a previous universe, like fingerprints pressed into the fabric of space-time. This isn't just poetic speculation. The math reveals a startling elegance. The infinite future and the infinitesimal past could be two sides of the same coin. Imagine crumpling a sheet of paper into a ball, then smoothing it out again. The wrinkles vanish, but the material remains. Similarly, the universe's expansion and eventual decay might erase all traces of structure, resetting the stage for a new quantum fluctuation to ignite another Big Bang. It's a vision where entropy, the arrow of time, isn't a one-way street but a loop, with each cycle offering a clean slate. But how does tunneling make this possible? In the quantum fog between eons, the universe wouldn't follow classical rules. Instead, it would exist in a superposition of states, both ending and beginning, until a probabilistic leap crystallizes the next eon. Think of it as a cosmic dice roll, where the outcome isn't a new universe from nothing, but a reincarnation of energy reshuffled into fresh forms. Critics argue this stretches quantum mechanics beyond recognition, but Penrose's audacity challenges us to rethink not just origins but endings. If he's right, the night sky isn't just a graveyard of dead stars, it's a gateway to countless past universes, their secrets encoded in light older than time itself. And somewhere beyond the edge of our imagination, another eon might already be stirring, its fate written in the same quantum rules that birthed us. What if our universe is nothing more than a cosmic projection, a three-dimensional illusion encoded on a two-dimensional surface at the very edge of reality? This is the holographic principle, an idea so radical it redefines what existence even means. And when you weave quantum tunneling into the mix, things get even stranger. Imagine the birth of our universe not as an explosion of matter, but as a quantum leap of information, a flicker of data tunneling from a flat, primordial surface into the fullness of space and time we experience today. The holographic principle emerged from a stunning revelation about black holes. When matter falls in, it doesn't just vanish. According to quantum mechanics, information can't be destroyed, so physicists like Gerard T. Hooft and Leonard Susskind proposed that all the data about swallowed stars gets smeared onto the black hole's event horizon like ink on a balloon. Stretch this idea to the cosmos, and suddenly, our entire universe might just be a vast, vibrating hologram, with every galaxy, every atom, encoded on a distant, two-dimensional boundary we can't see. Now layer quantum tunneling onto this framework. If the universe is fundamentally information, then its birth could have been a quantum jump, a transfer of data from one state to another. Picture a DVD containing every detail of a movie. The film exists as flat, microscopic pits on the disc's surface, but when you play it, it blossoms into a world of depth and motion. Similarly, our universe might have played its first frames when quantum fluctuations tunneled a two-dimensional code into three dimensions. It's as if reality booted up from a cosmic hard drive with the Big Bang as its startup chime. The math behind this is dizzying. In string theory, holography suggests that the fabric of space-time isn't the foundation of reality but a secondary effect, like the glow of a screen masking the pixels beneath. Quantum tunneling could be the mechanism that rendered this projection, bridging the gap between a flat quantum code and the textured universe we inhabit. Think of it as reality performing a magic trick. The universe you see is the rabbit pulled from the hat, but the real action happened in the hidden, two-dimensional folds of the magician's sleeve. Here's where it bends the mind further. If this theory holds, then black holes aren't just cosmic vacuum cleaners, they're clues. Their event horizons might be mirrors of the primordial surface from which our universe emerged. Some physicists speculate that black holes could even be tunneling points, gateways where information slips between dimensions. It's a haunting thought. Every black hole might contain a shard of the original hologram, a fragment of the code that birthed everything. But the wildest implication, this might solve one of physics' biggest puzzles, how gravity and quantum mechanics fit together. In the holographic view, gravity isn't a fundamental force but a side effect of quantum information interacting on the boundary. Quantum tunneling could be the glue stitching these realms together, a hidden process that allows the flat and the voluminous to coexist. So next time you look at the night sky, consider this. The stars might not be distant suns, but pixels in a projection so vast, so precise, that even our thoughts are part of the display. And somewhere on the edge of everything, the universe's original code still hums, waiting, perhaps, for another quantum jump. String theory doesn't just suggest alternate universes, it predicts a landscape of them, a vast cosmic quilt with 10 to the power of 500 possible patches, each stitched together by quantum tunneling. That's not a typo, 10 with 500 zeros after it, a number so large it dwarfs every atom in the observable universe. And nestled somewhere in that infinite tapestry is our reality, a single thread in a weave of unimaginable complexity. At the heart of this idea is something called the string theory landscape, a mind-bending concept where the fundamental constants of physics, the strength of gravity, the mass of electrons, even the number of dimensions aren't fixed laws but variables. Imagine a cosmic control panel with sliders for every force and particle, each setting corresponding to a unique universe. Most combinations would be sterile, universes where atoms never form or where black holes bloom like flowers. But a rare few, purely by chance, land in the sweet spot for life. Ours is one of those lottery winners. So how does quantum tunneling fit in? In this landscape, universes aren't static. They're dynamic, bubbling entities that can shift between configurations like a kaleidoscope turning. Picture a marble rolling through a mountain range with endless valleys. Each valley represents a stable universe, a place where physics settles into a workable balance. But quantum mechanics allows that marble to tunnel through mountains instead of rolling over them, jumping from one valley to another. In cosmic terms, this means a universe could spontaneously rewrite its own laws, transitioning from one vacuum state to another. It's as if the universe woke up one day and decided gravity should be stronger, or that time should flow backward. The implications are staggering. If tunneling between vacuum states is possible, our universe might not even be in its original configuration. It could have started with 11 dimensions, then shed 7 of them like a snake shedding skin. Or perhaps dark energy isn't a constant but a temporary phase, a pit stop on the way to another quantum leap. Some theorists even speculate that the mysterious cosmic inflation that jump-started our Big Bang was itself a tunneling event, a universe lurching from one energy state to a lower, more stable one, releasing enough energy to ignite reality as we know it. But here's the twist: if universes can tunnel, they might also collide. In the string theory landscape, neighboring bubbles could brush against each other, leaving scars in the cosmic microwave background, subtle ripples that hint at other realities just beyond our own. It's like hearing whispers through a wall, echoes of universes with entirely different rules. Some models even suggest that the Higgs field, which gives particles mass, might be sitting in a false vacuum, teetering on the edge of another tunneling event that could rewrite physics overnight. What does this mean for us? If the landscape is real, our existence isn't just unlikely, it's inevitable. With 10 to the 500 possibilities, some universe had to be hospitable, and we're the ones living in it. But it also raises a chilling question. If the constants of nature aren't constants at all, how stable is our corner of the landscape? Could another quantum jump undo the very fabric of our reality? For now, it's a mystery written in the language of vibrating strings, and the answer might be hiding in the spaces between dimensions. At the smallest scales imaginable, far beneath atoms, quarks, even the tiniest ripples of energy, spacetime isn't smooth. It's a seething, turbulent foam bubbling with quantum chaos. This is the Planck scale, where distances shrink to 10 to the minus 35 meters, and time fractures into slices of 10 to the minus 43 seconds. Here, gravity and quantum mechanics wage war, bending the rules until reality itself becomes a roiling sea of virtual particles, wormholes, and black holes flickering in and out of existence like cosmic static. And according to this theory, it's in this froth that universes might be born, not from a cataclysmic bang, but from a quiet quantum whisper. Picture spacetime foam as an ocean during a storm. Waves crash, bubbles form and pop, except these bubbles aren't made of water, but of raw possibility. In this chaos, tiny regions of space can tunnel into entirely new configurations, warping energy and curvature until they pinch off into self-contained universes. It's like blowing soap bubbles, but instead of soap film, the walls are woven from the fabric of spacetime itself. Some of these bubbles collapse instantly, while others, through sheer quantum luck, inflate into full-fledged cosmos. Our universe, just one bubble that grew large enough to escape the foam. The math behind this is dizzying. At the Planck scale, Heisenberg's uncertainty principle runs wild. Energy fluctuates so violently that microscopic black holes pop into being, evaporate in nanoseconds, and in their death throes could spit out baby universes. Nobel laureate Roger Penrose speculated that these quantum black holes might not be in points, but portal seeds for new spacetime to sprout. Imagine a dying star collapsing into a singularity, but instead of vanishing, it performs a quantum pivot, tunneling into an expanding universe of its own. It's cosmic mitosis on a scale we can barely fathom. Here's where it gets wilder. If spacetime foam births universes, those universes inherit their own quantum foam, meaning the process could repeat endlessly. Each new cosmos becomes a potential factory for more, like a chain reaction in a cosmic bubble bath. And because quantum tunneling doesn't follow strict cause and effect, these universes wouldn't need a shared timeline. Some might exist parallel to ours, others buried in layers we'll never see. But how could we ever test such a theory? Clues might hide in the faintest signals of the cosmos. Some physicists hunt for imprints of Planck-scale turbulence in gravitational waves, ripples that could carry echoes of spacetime's foamy origins. Others suggest high-energy particle collisions might, for a split second, recreate conditions where quantum gravity dominates, offering a glimpse into the froth. It's like trying to photograph the wake of a single bubble in a hurricane, but the stakes couldn't be higher, proof that our universe is just one eddy in an infinite quantum ocean. What's truly humbling is realizing how fragile our cosmic perspective might be. The galaxies we see, the laws we cling to, all could be the fleeting aftermath of a quantum fluctuation in a realm where time and space are barely concepts. And if this theory holds, the universe isn't a once-in-a-lifetime event. It's just another ripple in the foam, one of countless others fizzing into existence, each with its own version of reality. So the next time you stare at the night sky, remember, you might be looking at the aftermath of a quantum hiccup, a fleeting bubble in a sea of infinite possibilities. What if our universe wasn't born from nothingness, but from the crushing depths of a black hole in another reality? This is the black hole genesis hypothesis, a theory so daring it suggests every cosmic horizon might be a doorway to creation. Picture a supermassive black hole in some distant universe, its singularity stretching space-time into infinite density. But instead of ending in oblivion, that singularity could have tunneled through a quantum loophole, birthing an entirely new cosmos in its wake. Our universe in this scenario might just be the offspring of a collapsed giant from another dimension. At first glance, it sounds like science fiction. But the math tells a different story. When matter collapses into a black hole, it doesn't just vanish. Einstein's equations hint that the singularity at its core isn't a dead end, it's a bridge. NTHE Chinese letter LY warped geometry of a singularity. The fabric of reality could twist so violently that quantum effects take over, allowing a tunnel to another spacetime. Think of it like squeezing a balloon until it pops, except instead of air, the pressure releases an entire universe. This idea ties neatly into the work of physicists like Nikodem Poplawski, who proposed that the inward collapse of a black hole could rebound outward in another reality, a cosmic bounce fueled by quantum tunneling. The numbers suggest something astonishing. The conditions inside a black hole's singularity mirror those of the Big Bang itself. Infinite density, infinite curvature. It's as if the universe encoded the same recipe for creation in both destruction and birth. And here's where it gets wilder. If our universe spawned from a black hole, that black hole must reside in a parent universe with its own laws of physics. That means our cosmos could be nestled inside a grander multiverse, like a Russian doll of realities, each with its own black holes birthing new worlds. Some of those universes might have stronger gravity, faster light, or extra dimensions, endless variations forged in the hearts of dying stars. But how would we ever prove this? Clues might hide in the cosmic microwave background. If our universe inherited quantum fluctuations from its parent black hole, subtle asymmetries in the afterglow of the Big Bang could carry fingerprints of that ancestral collapse. Others speculate that spinning black holes might imprint a preferred direction on their offspring universes, a cosmic spin we could detect in the alignment of galaxies. The implications are staggering. If black holes are cosmic wombs, then every galaxy's heart might hold the seeds of new realities. And somewhere out there, in the depths of a supermassive black hole we'll never see, another universe could be flickering to life, a testament to the strange, boundless creativity of quantum tunneling. So next time you hear about a black hole devouring a star, remember, it might not be an end, but a beginning in disguise. Picture two sheets of paper floating in an empty room, flat, infinite, and perfectly parallel. Now imagine these aren't just sheets, but entire universes, each with their own stars, galaxies, and laws of physics. This is the heart of the ekpyrotic brane theory, where our cosmos isn't born from a singular explosion, but from a cataclysmic collision between these higher dimensional planes. And the twist, quantum tunneling might be the secret force that nudged them together, igniting the Big Bang as we know it. In M-theory, the grand framework that unites string theory's disparate branches, these sheets are called branes, short for membranes. They're not just three-dimensional like our universe, but vast, multidimensional surfaces vibrating through an 11-dimensional void. Normally, they drift apart, repelled by dark energy or other forces. But here's where quantum tunneling defies intuition. Even with energy barriers keeping them separate, there's a tiny probability the branes could suddenly, spontaneously collide. It's like two magnets held just far enough apart to repel, yet somehow snapping together against the odds. the aftermath of such a collision would be spectacular. When these branes smash, their kinetic energy doesn't just vanish, it transforms. The impact could heat the brane surfaces to unimaginable temperatures, creating a fireball so intense it mimics the conditions of the Big Bang. Matter, radiation, even space-time itself might emerge from the wreckage like sparks flying from a hammer striking an anvil. And here's the eerie part: this might not be the first time it's happened. The ekpyrotic model suggests these collisions could be cyclical, with branes eternally ricocheting apart and tunneling back together in an endless cosmic dance. But how does tunneling bridge the gap between separation and collision? In quantum terms, the branes don't need to overcome the energy barrier step by step. Instead, they teleport past it, borrowing energy from the vacuum of higher dimensions to make the leap. Think of it as a cosmic game of chicken where the branes don't swerve. They blink out of one position and reappear already entangled. The math behind this is staggering, blending quantum field theory with general relativity to describe how multidimensional objects might cheat classical physics. Critics argue this stretches M-theory's speculative foundations even further, but supporters point to tantalizing clues. If the ekpyrotic model is correct, the cosmic microwave background might carry faint bruises from the brane collision, subtle patterns in the afterglow that other Big Bang theories can't explain. Others speculate that gravitational waves, those ripples in spacetime from black hole mergers, could hold echoes of the original impact like seismic waves from a primordial earthquake. What's truly mesmerizing is the implication. Our universe might be one scar among many, a single crash site in an 11-dimensional highway where branes occasionally intersect. And if tunneling can trigger one collision, who's to say it hasn't happened elsewhere, birthing other universes with entirely different rules? It's a humbling thought that everything we know might be the fallout of a quantum accident in a dimension we'll never see. Time crystals, an idea so radical, even their discoverer initially thought they were impossible. These aren't gems you'd find in a cave, but structures that pulse in a repeating pattern without losing energy, like a perpetual motion machine that defies the universe's usual march toward chaos. Now, imagine if the cosmos itself began as one of these eerie quantum oddities, its earliest moments ticking like clockwork in a cycle of creation and rebirth. This is the time crystal universe hypothesis, where quantum tunneling didn't just spark the Big Bang, it locked reality into an eternal rhythm, a cosmic heartbeat woven into the fabric of spacetime. The magic lies in how time crystals break symmetry. Normally, the laws of physics treat all moments equally, no instant is special, but time crystals inherently pick out a rhythm, a pulse that repeats indefinitely even in their ground state. Nobel laureate Frank Wilczek first toyed with this idea in 2012, suggesting matter could organize not just in space but in time. Fast forward to 2017, and labs actually built them using chains of ions or nitrogen vacancies in diamonds, proving these bizarre states exist. Now, theorists like Xiao Gang propose something even grander, that the infant universe wasn't a fireball, but a fractal-like time crystal whose quantum vibrations tunneled into the explosive growth we call the Big Bang. Picture a cosmic metronome. In this model, the pre-Big Bang universe wasn't empty, it was a crystalline lattice oscillating between states, each tick and tock governed by quantum rules. Then, through tunneling, one of these oscillations breached an energy barrier, shattering the crystal's perfect rhythm and releasing a tsunami of energy that became space-time and matter. It's like winding a music box too tight until the spring snaps, unleashing a new kind of order from the wreckage of the old. The kicker: if the universe retains even a faint echo of this primordial ticking, the Big Bang might not have been a one-time event. Instead, it could be one note in an endless symphony, with each cycle birthing a slightly altered version of reality. Evidence could lurk in the cosmic microwave background. If the universe inherited fluctuations from a time crystal structure, the afterglow of creation might carry imprints of that regularity, subtle patterns that repeat like grooves on a vinyl record. Others speculate that dark matter, that mysterious substance holding galaxies together, might be composed of time crystal remnants, their rhythmic nature untouched by the chaos of the expanding cosmos. What's truly unsettling is the implication. If the universe is a time crystal at heart, then entropy, the arrow of time we assume always points toward disorder, might be an illusion. Beneath the surface, reality could be locked in a loop, tunneling between states in a dance that never truly ends. It's a vision where the cosmos isn't just expanding but breathing, and the next quantum leap might already be counting down. What if universes, like living things, are subject to their own version of natural selection, where only the ones capable of birthing new realities survive? This is the radical premise of quantum Darwinism, a theory that twists the rules of biology into the fabric of cosmology. Instead of genes passing traits to offspring, imagine quantum tunneling events acting as cosmic DNA, favoring universes that can reliably reproduce through their own collapse and rebirth. In this wild scenario, the very laws of physics might not be arbitrary, but honed by an unseen evolutionary pressure where universes that tunnel effectively into new states outcompete those that don't. Think of it as survival of the fittest on a multiversal scale. Just as animals adapt to their environments, universes could evolve toward configurations that maximize their ability to spawn offspring through black holes, brane collisions, or vacuum fluctuations. The math behind this is dizzying. Certain constants, like the strength of gravity or the mass of the Higgs boson, might be finely tuned not by chance, but because these values increase the odds of a universe reproducing. For example, a cosmos with slightly stronger gravity might form more black holes, each one a potential seed for a new reality through quantum tunneling. Over countless generations, universes with these reproductive advantages would dominate the multiverse landscape while sterile ones fade into oblivion. The parallels to biology are uncanny. Just as dolphins evolved streamlined bodies to navigate oceans, universes could have evolved stable nuclear forces to forge the heavy elements needed for black holes. Even the mysterious dark energy accelerating our universe's expansion might not be random. It could be a trait ensuring enough space between galaxies for black holes to form without interference. Lee Smolin, one of the theory's pioneers, likens it to a cosmic ecosystem where black holes are the reproductive organs of spacetime, funneling quantum information into new dimensions. Critics argue this verges on circular reasoning. Why assume universes need to reproduce at all? But supporters counter that quantum Darwinism solves the fine-tuning problem without invoking luck or deities. If universes are selected for fertility, our existence isn't a miracle. It's inevitable in a lineage of cosmos optimized for creation, and the evidence might be hiding in plain sight. If our universe is part of this evolutionary chain, its laws should favor processes that generate black holes, and indeed, stars massive enough to collapse into them are common, while conditions preventing their formation, like overly weak gravity, are absent. The most mind-bending implication: if this theory holds, the multiverse isn't a static collection of random bubbles, but a living, branching tree where each universe inherits traits from its predecessors. Quantum tunneling isn't just a quirk of particles, it's the mechanism of cosmic inheritance, weaving causality across dimensions. So next time you gaze at a black hole's abyss, consider you might be staring at the cradle of a new universe sculpted by eons of unseen selection. And somewhere in its depths, the next iteration of reality could already be stirring. Among all the bizarre consequences of quantum physics, few are as unsettling as the Boltzmann brane paradox, a thought experiment that suggests your entire existence, your memories, even the world around you, might be nothing more than a fleeting illusion conjured from random quantum fluctuations. And here's the chilling twist: quantum tunneling could be the very mechanism making this nightmare scenario possible. the paradox traces back to Ludwig Boltzmann, a 19th-century physicist who wrestled with entropy, the universe's tendency toward disorder. He realized that given enough time, even the most improbable events become inevitable, like a room full of monkeys eventually typing Shakespeare. Apply that to quantum vacuum fluctuations, and the math suggests something eerie. In the vast emptiness of space, particles can spontaneously arrange themselves into complex structures, including self-aware minds. Not over billions of years right now, a fully formed brain, complete with false memories of a past that never existed, could flicker into existence from pure nothingness. And thanks to quantum tunneling, it wouldn't even need to wait for random chance. Particles could cheat, tunneling through energy barriers to assemble a conscious observer in an instant. Think of it like this: the vacuum of space isn't truly empty. It's a seething foam of virtual particles popping in and out of existence, borrowing energy from nowhere. Most of these fluctuations vanish as fast as they appear, but tunneling changes the game. Normally, the odds of particles arranging into something as intricate as a brain are astronomically low, like rolling a million dice and having them all land on 6. Quantum tunneling, though, lets the dice skip the rolling entirely, teleporting straight to the desired outcome. Suddenly, Boltzmann brains aren't just improbable, they're inevitable. This isn't just philosophical hand-wringing. The paradox exposes a glaring tension between quantum mechanics and cosmology. If the universe is eternal or cyclical, as many theories suggest, then Boltzmann brains should outnumber real observers like us by an unimaginable margin. After all, it's far easier for randomness to conjure a single floating brain than an entire universe with galaxies, planets, and coherent history. So why does reality feel so real? Some physicists argue this very paradox disproves eternal universes because if they were true, you'd statistically be a Boltzmann brain, adrift in the void, hallucinating everything. Others propose that quantum decoherence, the process that prevents tunneling from running amok, acts as a cosmic filter, suppressing these rogue observers. But the most unsettling solution: there's no solution. We might already be Boltzmann brains, our sense of reality just a fleeting glitch in an indifferent cosmos. The takeaway isn't despair, but humility. If quantum tunneling can make existential nightmares mathematically plausible, then our grasp on reality is far shakier than we thought. And yet, here we are debating, exploring, reaching for answers. Maybe that's the ultimate rebuttal. A Boltzmann brain wouldn't waste time questioning its existence. It would just be. The fact that we're even having this conversation might be the best evidence that we're real after all. Or is it? What if our universe isn't just governed by quantum tunneling, but designed around it? This is the simulation hypothesis with a twist, that the bizarre, rule-breaking behavior of particles at the quantum level isn't a bug in reality's code. It's the signature of a programmer's handiwork. Imagine a universe built in some unfathomable computer, where tunneling isn't a quirk of physics but a deliberate shortcut to optimize processing power. After all, if you're simulating trillions of particles, wouldn't you cheat by letting them occasionally teleport past barriers instead of calculating every collision? This idea takes the classic simulation argument, the notion that our reality might be an artificial construct, and injects quantum mechanics into its veins. Proponents like Nick Bostrom suggest that advanced civilizations could run ancestor simulations so detailed, their inhabitants like us would never know the difference. But here's the kicker: if such simulations exist, they'd need to conserve computational resources. Quantum tunneling offers the perfect loophole. Instead of painstakingly simulating every possible path a particle might take, the program could simply allow improbable jumps, saving processing cycles. It's like a video game rendering only what the player sees, letting distant objects pop into existence when needed. Think about how glitches work in software. Sometimes characters clip through walls not because the physics engine failed, but because the system prioritizes speed over precision. Now apply that to reality. Particles tunneling through barriers might be the cosmic equivalent of a rendering shortcut, a way for the simulation to handle extreme scales without overloading. Even the probabilistic nature of quantum mechanics fits this narrative. Uncertainty isn't a limitation of our knowledge, it's a feature, a way to avoid calculating definitive states until absolutely necessary. Schrödinger's cat isn't both dead and alive. The simulation just hasn't rendered the outcome yet, but here's where it gets eerie. If tunneling is a programmed feature, it could leave detectable fingerprints. Just as a video game's frame rate drops when too much happens at once, a simulated universe might show computational limits at extreme energies. Some physicists speculate that high-energy particle collisions could reveal pixelation in space-time, tiny, discrete steps in energy or position where the simulation rounds off numbers to save resources. Others suggest that quantum entanglement, where particles instantly influence each other across distances, might be a form of non-local rendering, a cheat to avoid updating distant objects independently. Of course, this raises a haunting question. If we're in a simulation, who's running it? Are we someone's science experiment, an ancestor simulation, or even an art project? And more unsettling, could the programmers intervene? Quantum tunneling events might be more than random. They could be patches, updates, or even messages woven into the fabric of reality itself. So next time you hear about an electron vanishing through a wall, consider this. It might not be physics at all. It might just be the universe's source code running exactly as intended. Dark energy might be the universe's biggest unsolved mystery, an invisible force pushing galaxies apart faster and faster, as if reality itself has its foot on the accelerator. But what if this mysterious energy isn't just some abstract field? What if it's the cosmic aftermath of a quantum tunneling event so colossal, it rewrote the rules of space-time? This theory suggests dark energy is no accident, it's the lingering echo of a quantum phase transition, a moment when the universe tunneled through an energy barrier and emerged as something entirely new. Think of it like ice cracking under pressure. Water molecules normally freeze into a rigid pattern, but under extreme conditions, they can suddenly shift into a different arrangement, a phase transition. Now imagine that happening to the fabric of reality itself. In the universe's infancy, quantum fields might have existed in a higher energy state, like a stretched rubber band. Then, through tunneling, one of those fields snapped into a lower energy configuration, releasing pent-up energy that now drives cosmic expansion, the kicker. This wouldn't have been a slow melt, but a quantum leap, an instantaneous, probabilistic jump that left behind dark energy as its fingerprint. This idea ties into something called vacuum energy. According to quantum field theory, empty space isn't empty. It's a seething soup of virtual particles popping in and out of existence. Most of their energy cancels out, but if a quantum field tunneled into a new state, even a tiny leftover could explain dark energy's relentless push. It's like a room full of people shuffling normally. Their movements balance out, but if everyone suddenly took one step forward, that collective nudge would be unstoppable. On a cosmic scale, that nudge is dark energy, the universe's quantum hangover from an ancient transition. The math behind this is both elegant and haunting. If this phase transition happened early enough, its energy would have been diluted by expansion, just as we observe. And unlike other dark energy theories, tunneling provides a mechanism for why the transition occurred at all. Quantum fields don't need to roll downhill like a ball. They can teleport past barriers, sidestepping classical limits. Some models even suggest this tunneling event wasn't unique. Multiple fields could have transitioned at different times, layering effects that shaped cosmic history. But here's where it gets eerie. If dark energy is a remnant of quantum tunneling, it might not be constant. Just as ice can refreeze under new conditions, the universe's vacuum might yet tunnel again. Some physicists speculate that dark energy's slight variations over time could hint at this instability, a sign that another transition lurks in our future. Picture a universe where dark energy suddenly shifts, rewriting the strength of gravity or the speed of light overnight. It's a reminder that the cosmos, for all its seeming permanence, might still be balancing on a quantum knife's edge. The most profound implication: this theory blurs the line between the quantum and the cosmic. A subatomic process tunneling could dictate the fate of galaxies, proving once again that the universe's greatest mysteries are often its smallest secrets writ large. So when you hear about dark energy accelerating the cosmos, remember, you might be witnessing the ghost of a quantum leap that happened billions of years ago, one that's still shaping everything we see. Neutrinos are the universe's most elusive ghost particles, so tiny and weakly interacting that trillions pass through your body every second without leaving a trace. But what if these cosmic phantoms aren't just passive bystanders? What if they played a starring role in the universe's birth? This theory suggests that in the earliest moments of existence, neutrinos didn't just wander aimlessly. They formed a vast, exotic condensate, a quantum sea so dense and strange that its sudden phase transition could have triggered cosmic inflation, setting the stage for everything we see today. Picture the infant universe not as a blazing fireball, but as a superfluid, a frictionless, ultra-cold medium where particles move in perfect unison. Under extreme heat and pressure, neutrinos, which normally ignore each other, might have condensed into this bizarre state, like dew forming on a leaf. Then, as the cosmos cooled, this neutrino condensate could have undergone a quantum phase transition, tunneling from one state to another in an instant. The energy released would have been staggering, like an ice sheet cracking across the entire universe, unleashing the explosive expansion we call inflation. It's a twist on the standard Big Bang narrative, one where the universe didn't just inflate randomly, but was pushed by the sudden reorganization of its most mysterious particles. The math behind this is as elegant as it is bold. Neutrinos, despite their reluctance to interact, have mass, a discovery that won the Nobel Prize in 2015. In the early universe's extreme density, their combined gravitational pull could have been significant. Some models suggest that as they condensed, their collective behavior changed, flipping a cosmic switch that released latent energy stored in the quantum vacuum. This energy wouldn't just nudge inflation, it could drive it, like a piston firing in the engine of creation. Here's where it gets even wilder. If neutrinos formed such a condensate, their quantum properties might still echo in the cosmos today. The large-scale structure of the universe, the vast web of galaxies and voids, could bear the imprint of their primordial dance. Even more tantalizing, relic neutrinos from this phase might still exist, drifting through space as a fossilized whisper of that ancient transition. Detecting them would be like finding the footprints of the universe's first quantum leap. But why neutrinos? Why not other particles? The answer lies in their uniqueness. Unlike quarks or electrons, neutrinos ignore almost all forces, making them immune to the chaos of the early universe. This independence could have allowed them to coalesce into a condensate while other particles were still trapped in the firestorm. It's as if the universe, in its infancy, entrusted its most delicate task to the only particles quiet enough to listen. This theory isn't without controversy. Critics argue that neutrinos' weak interactions make them unlikely candidates for such a pivotal role. But supporters counter that in the extreme conditions of the early cosmos, rules we take for granted might not apply. Quantum tunneling, after all, thrives on the improbable. And if a neutrino condensate did trigger inflation, it would solve a major puzzle: why inflation started in the first place. Rather than relying on a mysterious inflaton field, the universe could have used particles we already know exist, turning its shyest actors into the architects of reality. So next time you hear about neutrinos, remember, they might be more than cosmic background noise. They could be the silent conductors of the universe's first symphony, their quantum rhythms still vibrating through the fabric of space-time. And somewhere out there, in the echoes of their ancient condensate, the secret of our origins might still be waiting to be found. Among all the hypothetical particles in physics, actions might be the most poetic, ghostly wisps of matter theorized to solve mysteries from dark matter to the strong force, yet never directly detected. But what if these elusive particles didn't just wander the cosmos passively? What if, in the universe's earliest moments, they orchestrated its very structure through a quantum tunneling event so profound, it sculpted the cosmic web we see today? This is the action field collapse hypothesis, where the birth of galaxies, stars, and even the voids between them might trace back to a single, silent quantum leap in the dark. Picture the infant universe during inflation, a trillionth of a second old, expanding faster than light, its energy field seething with potential. Among these fields, one stood apart, the action field, a hypothetical sea of energy tied to these enigmatic particles. Unlike the Higgs field, which gives particles mass, the action field would have been unstable, teetering on the edge of collapse like a sand dune before an avalanche. Then, through quantum tunneling, it happened. The field breached its energy barrier, cascading into a lower state and releasing ripples that would one day become galaxies. The mechanics are as elegant as they are strange. Actions, if they exist, are absurdly light, possibly 1 trillion times lighter than electrons, and interact so weakly with normal matter that they could pass through a light year of lead without a whisper. But in the dense furnace of the early universe, their collective behavior might have been cosmically transformative. As the action field tunneled, it wouldn't have just released energy, it would have imprinted quantum fluctuations onto spacetime itself. These fluctuations, stretched to macroscopic scales by inflation, became the gravitational seeds for everything: clusters of matter where the field collapsed more intensely, voids where it barely flickered. It's like throwing a handful of pebbles into a pond, then watching the ripples expand until they're the size of continents. The implications are staggering. If this theory holds, actions aren't just candidates for dark matter. They're the cosmic architects that dictated where dark matter and everything else would clump. Their tunneling event could explain why the universe isn't perfectly smooth, why galaxies cluster in filaments and sheets instead of scattering randomly. Even the slight unevenness in the cosmic microwave background, the afterglow of the Big Bang, might carry the action field's fingerprint, a quantum signature frozen in time. But how do you test such an idea when actions remain theoretical? The answer lies in their echoes. If actions permeate space today as dark matter, their residual vibrations could subtly influence the spin of atoms. Experiments like the Action Dark Matter experiment ADMS hunt for these whispers using supercooled magnets and quantum amplifiers, listening for the faintest hum of an action's presence. Others scour the skies for anomalies in starlight polarization, hunting for signs that actions bend light as it travels through galactic magnetic fields. The most tantalizing clue, though, might come from black holes. Some theories suggest spinning black holes could convert actions into detectable radio waves, a process called superradiance. If telescopes catch these signals, it would be like overhearing a conversation between the universe's birth and its present, a dialogue written in quantum tunneling's cryptic language. What's truly humbling is realizing how much of reality might hinge on particles we've never seen. The action field collapse theory suggests that the grand tapestry of galaxies, the very framework of existence, could owe its shape to a quantum shiver in an invisible sea. It's a reminder that the universe's greatest dramas often play out in realms beyond our senses, and that the key to understanding everything might be hiding in the quietest corners of physics. Supersymmetry is physics' most elegant idea that never quite came true, a theory so beautiful it had to be right, except for one problem: we've never found a shred of evidence it exists. Yet hidden in its mathematical heart might lie the key to the universe's first quantum tunneling event, the moment symmetry shattered, unleashing the forces that built reality as we know it. Picture a cosmic mirror where every particle has a perfect, unseen twin. Electrons pair with selectrons, quarks with squarks, photons with photinos, a shadow universe of superpartners balancing the scales of nature. That's supersymmetry's promise, a profound symmetry that would unite all forces under one mathematical roof. But here's the catch: if supersymmetry was real in the early universe, it didn't last. Something broke it, and that breaking, a cataclysmic shift in the quantum fields underpinning reality, might have been triggered by tunneling, sending ripples through space-time that shaped everything from gravity to the atoms in your body. How? Imagine a frozen lake at the cusp of spring. The ice is perfectly smooth, symmetrical, until one random vibration fractures it. Similarly, the supersymmetric universe existed in a pristine, high-energy state where particles and their twins were indistinguishable. Then, as the cosmos cooled, quantum fluctuations nudged a field called the super-Higgs toward an energy barrier. Classically, it should have stayed trapped, but tunneling doesn't play by classical rules. In an instant, the field leapt through the barrier, collapsing into a lower energy state and shattering the symmetry like glass. The fallout was cosmic. That collapse would have released colossal energy, warping space-time and splitting what was once a unified force into the four we recognize today: gravity, electromagnetism, and the strong and weak nuclear forces. It's as if a single frozen language suddenly fractured into dialects, each with its own rules, yet all tracing back to the same root. The strong force glued quarks together, the weak force sculpted radioactive decay, and electromagnetism lit the stars. Without this breaking, atoms couldn't form, chemistry wouldn't exist, and the universe would be a featureless sea of indistinguishable particles. But why tunneling? Because at those energies, thermal fluctuations alone couldn't overcome the barrier. The universe needed a quantum cheat code, a probabilistic leap past impossibility. Just as electrons teleport through walls in a lab, the super-Higgs field bypassed classical physics, rewriting the rules of reality in the process. Some models even suggest this tunneling event was cosmic inflation, the universe's explosive expansion driven by the energy of symmetry breaking. Here's the twist: if supersymmetry left echoes, they might still be detectable. The lightest superpartner, perhaps the photino or neutralino, could be dark matter lurking unseen because it only interacts via gravity. Others might materialize in particle colliders if we ramp up energies enough to glimpse the universe's pre-collapse state. Even gravitational waves could carry whispers of the event, ripples from a phase transition that birthed the forces holding your world together. So the next time you flip a light switch or feel gravity's pull, remember, you're witnessing the aftermath of a quantum dice roll, a split second when symmetry shattered and the universe chose chaos over perfection. And somewhere in the void, the particles we've never found might still be waiting, ghosts of a mirror world that shaped ours, then vanished without a trace. The very fabric of space and time might not always have been smooth and continuous. What if it started as a chaotic quantum network, a roiling sea of disconnected nodes, before suddenly crystallizing into the orderly dimensions we know today? This is the radical premise of quantum gravity, a theory where space-time isn't fundamental but emerges from something deeper, a vast, shifting web of quantum connections that froze into place through a tunneling event in the universe's first moments. Imagine throwing a handful of iron filings onto a table. At first, they scatter randomly, each piece isolated, but place a magnet beneath, and suddenly they align into elegant arcs, a pattern where none existed before. Quantum gravity suggests space-time underwent a similar transformation at the Planck epoch, that unfathomably brief sliver of time just 10 to the minus 43 seconds after the Big Bang. Before this moment, reality wasn't made of three spatial dimensions and time. It was a buzzing network of abstract quantum links, a cosmic fog where concepts like here and there had no meaning. Then, in a flash, this network tunneled through an energy barrier, locking into a stable, crystalline configuration, the four-dimensional spacetime we inhabit. The mechanics are mind-bending. In this model, the universe's building blocks aren't particles or strings, but nodes in a graph, connected by ever-changing links representing potential relationships. At ultra-high energies, these links fluctuate wildly, creating a soup where distance and direction are meaningless. But as the cosmos cooled, the system faced a choice: remain disordered or leap into a new state. Quantum tunneling provided the escape route, bypassing classical energy barriers to snap the network into an ordered lattice like water molecules suddenly aligning into ice. The critical twist: this lattice's structure defines spacetime itself. The links between nodes became the glue holding dimensions together, and their vibrations gave rise to matter and energy. It's as if the universe booted up from a quantum operating system with spacetime as its user interface. Why does this matter? Because it solves two colossal puzzles at once. First, it banishes the singularity, the infinitely dense point at the Big Bang that breaks physics. In quantum gravity, there's no singularity, just a phase transition where the network reconfigures. Second, it offers a quantum origin for gravity. The theory suggests gravity isn't a fundamental force but a side effect of the network's imperfections, like how cracks in ice create pathways for meltwater. Einstein's curvature of spacetime, just the cosmic lattice flexing under strain. The echoes of this transition might still be detectable. If spacetime crystallized unevenly, light traveling across the cosmos could carry faint scars, anisotropies in its polarization, or delays in gamma-ray bursts. Some models even predict defects in the lattice, cosmic strings left over from the phase change, which could warp spacetime like scratches on a lens. Others speculate that black holes might be places where the network melts back into disorder, portals to the universe's pre-geometric past. But the wildest implication: if spacetime emerged from a quantum network, it might not be unique. Other configurations could exist: universes with 2 dimensions, or 7, or none at all. Some might cycle between states, crystallizing and melting in eternal loops. And somewhere beyond our cosmic horizon, another lattice might hum with entirely different rules, a parallel reality built from the same quantum code but folded into unimaginable shapes. So the next time you glance at the clock or measure a distance, remember, the ticks and meters might just be relics of an ancient freeze, a quantum gamble that turned chaos into order. And the spacetime you take for granted, it's not the stage, it's the performance. Imagine the universe as a vast, ever-changing mosaic, not made of tiles, but of tiny geometric shapes constantly rearranging themselves into new patterns. This is the essence of causal dynamical triangulation, a daring approach to quantum gravity where spacetime isn't smooth and continuous, but a patchwork of microscopic triangles shifting in real time. And buried in this cosmic kaleidoscope lies a mind-bending possibility. That quantum tunneling doesn't just happen through space, but to space itself, allowing entire universes to leap between radically different geometries in an instant. At its core, this theory treats spacetime like a cosmic Lego set. Instead of the infinitely divisible fabric of Einstein's relativity, reality is built from finite, 4-dimensional blocks, specifically triangular prisms called simplices. These blocks connect along their edges, forming a dynamic network where time always flows forward, hence causal, but the arrangement of space is fluid. The magic happens when quantum fluctuations cause these simplices to spontaneously rearrange, flipping their connections like a deck of cards being shuffled. Most changes are minor, but occasionally the entire structure tunnels into a new configuration, a geometric phase transition so profound it could birth an entirely new spacetime geometry from the old. Think of it like ice crystallizing from water. Under normal cooling, water molecules gradually slow down until they lock into ice's hexagonal pattern. But if you supercool water suddenly, it can leap straight into a different crystalline form, bypassing the usual steps through quantum tunneling. In causal dynamical triangulation, space-time does something similar. As the universe cools from the Big Bang's inferno, its simplices don't just settle gently into our familiar four dimensions. Instead, they might tunnel past intermediate states, snapping directly into the geometry we observe today. It's as if the universe skipped several chapters in its own instruction manual, landing on the right page by sheer quantum luck. What makes this idea revolutionary is how it tackles gravity's greatest paradox. In Einstein's world, space-time bends smoothly like a rubber sheet under weight, but at quantum scales, that smoothness shatters into probabilistic chaos. Causal dynamical triangulation bridges this gap by making space-time granular yet dynamic. Each simplex is a tiny quantum decision point, and tunneling allows the whole system to explore every possible configuration simultaneously until one dominates. This could explain why we perceive a stable, classical universe despite its quantum foundations. The geometry we see isn't the only option, it's just the one that won the tunneling lottery. The implications are staggering. If space-time can tunnel between geometries, our universe might have undergone multiple such leaps before settling into its current form. Some configurations could have had extra dimensions that later compactified, or bizarre causal structures where time looped in knots. Others might have been stillborn, collapsing instantly under their own inconsistencies. This paints cosmic history not as a straight line, but as a branching tree of possible geometries, with our reality just one surviving limb, even wilder. This process might still be happening. Black holes, those cosmic wrecking balls, could be places where space-time simplices tunnel back into chaos, erasing dimensions like a collapsing house of cards. Wormholes, if they exist, might not be tunnels through space, but quantum shortcuts between geometric phases, and the mysterious dark energy accelerating the universe's expansion. It could be the faint tremor of simplices preparing for their next great leap. Detecting these geometric transitions would require probing space-time at the Planck scale, far beyond current technology. But subtle clues might linger in the cosmic microwave background's faint irregularities, or in the way gravity waves ripple across the universe. If we ever spot anomalies that defy smooth space-time's predictions, it could hint at the pixelated, tunneling reality beneath. So when you look up at the night sky, remember, the space between stars might seem empty and serene, but beneath the surface, it's a seething quantum construction zone where geometry itself is forever one tunneling event away from reinvention. Einstein's equations once predicted the existence of bizarre tunnels through space-time wormholes, bridges connecting distant points in an instant. But what if these cosmic shortcuts aren't just relics of relativity? What if they played a starring role in the birth of the universe itself? Enter the ER equals EPR conjecture, one of the most audacious ideas in modern physics, suggesting that quantum entanglement and wormholes might be two sides of the same coin, and that the universe's first quantum tunnel wasn't just a particle slipping through a barrier, but an entire space-time structure stitching itself into existence. Picture entanglement, that spooky phenomenon where particles instantaneously influence each other across vast distances, as if sharing a hidden connection. Now imagine that connection isn't abstract, but physical, a microscopic wormhole linking the particles through the fabric of space-time. This is the heart of ER equals EPR, a proposal by Juan Maldacena and Leonard Susskind that redefines entanglement as geometry. In this view, every entangled pair might be joined by a Planck-scale wormhole, a tunnel so tiny it's invisible even to our best instruments. But in the searing heat of the early universe, these threads could have woven something far grander, a network of wormholes so dense they became space-time itself. The implications for cosmic origins are staggering. If quantum entanglement and wormholes are truly equivalent, then the universe's first moments might have resembled a quantum foam, not just of particles, but of space-time bridges, countless tiny tunnels flickering in and out of existence. Most would collapse instantly, but through quantum tunneling, a rare few could stabilize, merging into a self-sustaining web. Like drops of water fusing into a pond, these primordial wormholes might have coalesced into the smooth continuum we call space-time, with the Big Bang marking the moment the network crystallized into permanence. This idea flips traditional cosmology on its head. Instead of space-time emerging from a singularity, it could have arisen from a quantum entanglement phase transition, a reorganization so profound, it birthed both geometry and matter in one swoop. Think of it as the universe bootstrapping itself into being, particles entangled, their wormhole links multiplying until the connections outnumbered the voids, and suddenly the abstract became tangible. The vacuum of space, just the afterglow of a wormhole network reaching critical density, the laws of physics, the emergent rules of entanglement writ large. But here's where it gets even wilder. If ER equals EPR holds, the universe didn't just use wormholes, it might still be made of them. Black holes, those gravitational monsters, could be knots where wormholes tangle into dead ends. Dark energy, the force accelerating cosmic expansion, might be the tension of the network stretching thin. Even the arrow of time could trace back to the one-way flow of quantum information through these space-time threads. It's a vision where the universe isn't just held together by gravity, but by an invisible lattice of tunnels we're only beginning to fathom. The echoes of this wormhole genesis might still be detectable. If the early universe was a froth of entangled connections, its remnants could linger in the quantum correlations between distant galaxies, subtle patterns waiting to be decoded. Others speculate that gravity waves from colliding black holes might carry imprints of their wormhole origins, like harmonics from a plucked cosmic string. So the next time you hear about quantum entanglement, remember, it might not just be a curious quirk of particles. It could be the ghostly whisper of the universe's first stitches, the threads that sewed nothingness into everything we know. And somewhere in the void, those threads might still be vibrating, a cosmic tapestry woven from the fabric of tunnels we're just learning to see. Could the very act of observation be what called the universe into existence? This isn't just philosophy, it's a radical twist on quantum mechanics that suggests reality might not exist in a definite state until someone or something observes it. And when you bring quantum tunneling into the picture, things get even stranger. Imagine the universe's first moments as a fog of infinite possibilities, a quantum soup where every potential outcome, every particle, every law of physics existed simultaneously in a shimmering haze of maybes. Then, through a cascade of observations, perhaps from the universe itself, those possibilities collapsed into the singular reality we know today. But here's the mind-bending part. Tunneling could have been the mechanism that allowed this collapse to happen. Think about the classic double-slit experiment, where particles behave as waves until observed, at which point they choose a definite state. Now scale that up to cosmic proportions. In the participatory universe hypothesis, the Big Bang wasn't just a random event. It was the first act of observation, a quantum measurement that locked in the universe's initial conditions. But how does tunneling fit in? Quantum tunneling is, at its core, a probabilistic phenomenon. Particles don't follow predictable paths but jump unpredictably across barriers. If the early universe was a superposition of states, tunneling could have been the bridge that allowed one particular configuration to win, selected by some primordial act of observation. It's as if the universe rolled a quantum die, and the moment it landed, reality crystallized around the result. This idea ties into John Wheeler's famous participatory anthropic principle, which suggests that observers are necessary to bring the universe into being. But it doesn't require human consciousness. Any interaction that collapses quantum uncertainty could count. In the chaotic plasma of the early cosmos, particles constantly interacting with each other might have acted as rudimentary observers, tunneling from one state to another and, in the process, defining the laws of physics. Picture a room full of Rube Goldberg machines, each trigger dependent on the last. One quantum fluctuation tunnels into existence, which prompts another and another, until the entire structure of reality emerges from the noise. The implications are staggering. If observation and tunneling shape the universe, then the constants of nature, the speed of light, the strength of gravity might not be fundamental truths but frozen accidents, quantum possibilities that won the observation lottery. It also raises eerie questions about fine-tuning. Is the universe suited for life because life ultimately participated in its creation? Some interpretations even suggest that advanced civilizations in the future could, through observation, retroactively influence the universe's birth, a loop where the end reaches back to shape the beginning. Critics argue this veers into metaphysics, but the math holds surprising weight. Quantum decoherence, the process by which superpositions collapse into definite states, bears a striking resemblance to tunneling dynamics. Both involve systems transitioning from uncertainty to stability, just on vastly different scales. And if space-time itself is emergent from quantum interactions, as some theories propose, then the participatory universe might not be so far-fetched after all. So the next time you look up at the stars, consider this. The light reaching your eyes isn't just a passive signal from the cosmos. It might be part of an unbroken chain of observation stretching back to the first quantum flicker of existence, a universe that only became real because something somewhere was there to see it. Time might feel like an unshakable constant, an arrow flying forever forward, but what if it's just an illusion, a side effect of something far stranger happening behind the scenes? The thermal time hypothesis dares to suggest that time isn't fundamental at all. Instead, it emerges from the chaotic dance of quantum particles, a mirage woven from entanglement and energy flow. And here's where quantum tunneling crashes the party. If time isn't built into the universe's foundation, its arrow could have been set in motion by a single, universe-altering tunnel through the quantum fog. Picture the pre-Big Bang cosmos not as a void, but as a timeless quantum soup, a place where past, present, and future blur into a single superposition. Without entropy or energy gradients, there's no before or after, just frozen potential. Then, like a needle skipping across a record, quantum tunneling jolts the system. A single particle, or perhaps an entire field, breaches an energy barrier it shouldn't overcome, creating the first irreversible event. That moment, that first quantum cheat, breaks the symmetry. Suddenly, there's a before and after. Energy begins to flow, entropy stirs, and time, as we know it, flickers to life like a candle in the dark. This idea ties into Carlo Rovelli's groundbreaking work on quantum gravity, where he proposed that time isn't a dimension but a statistical illusion, much like temperature isn't a property of individual atoms but a collective behavior. In this view, clocks don't measure some universal tick. They track quantum correlations, the way particles interact and entangle. But for those correlations to form, something had to break the initial symmetry. Enter quantum tunneling, the cosmic dice roll that tilted the first domino, setting the stage for cause and effect. Think of it like a deck of cards. In a perfectly ordered deck, every shuffle looks the same. There's no arrow of time. But once you randomize it, the sequence becomes irreversible. Quantum tunneling could have been the universe's first shuffle, the moment it transitioned from timeless order to dynamic chaos. And the evidence might be written in the oldest light we can see. The thermal fluctuations in the cosmic microwave background, those faint temperature variations, aren't just random noise. They could be quantum tunneling's fingerprint, the first whispers of time's arrow echoing across 14 billion years. But here's the twist: if time is thermal, not fundamental, it might not flow the same everywhere. Near black holes or in the early universe's extreme conditions, quantum effects could warp or even suspend time's flow. It's a notion that bends the mind that the steady tick of your watch isn't universal law, but a local phenomenon as fleeting as a gust of wind in an infinite storm. So the next time you check the clock, remember, you might not be measuring time's passage, but the aftermath of the universe's first quantum leap, a single, improbable tunnel from stillness to story. And somewhere in the quantum foam, the echoes of that jump might still be ringing, a silent heartbeat beneath the skin of reality. In the bizarre realm of quantum mechanics, every decision you make, every choice, every observation, might not just alter your future, but spawn an entirely new universe where the opposite happened. This is the many worlds interpretation, a vision of reality where every quantum possibility plays out somewhere in an ever-branching multiverse. But what breathes life into these parallel worlds? What stitches them into existence? The answer might lie in quantum tunneling. The same phenomenon that lets particles vanish through walls could be the cosmic needle weaving the fabric of countless realities. Picture a single electron orbiting an atom. In classical physics, it's a tiny planet tracing predictable paths, but quantum mechanics paints a stranger portrait. The electron exists as a probability cloud, a haze of could-be locations. When you measure it, that cloud collapses to a single point, or so we thought. The many worlds interpretation flips the script. There's no collapse. Instead, the universe splits. In one branch, you see the electron here. In another, it's there. Both outcomes are real. Both universes proceed, forever unaware of each other. Now imagine this happening not just for electrons, but for every quantum event, every particle spin, every radioactive decay, every choice at the quantum crossroads. The result, a fractal tree of universes, each branch a new timeline with its own version of history. Quantum tunneling slips into this picture like a ghost in the machine. Normally, particles are confined by energy barriers like a ball trapped in a valley. But tunneling lets them escape without climbing, vanishing from one side and reappearing on the other as if the barrier wasn't there. In the many worlds framework, this isn't magic. It's the particle exploring all possible escape routes simultaneously across branching universes. In one world, it fails. In another, it tunnels. The act of tunneling is the universe splitting, each outcome realized in a separate timeline. This isn't just theoretical sleight of hand. Experiments like the double-slit experiment, where particles behave as waves unless observed, hint at this branching. When a particle's wave function encounters the slits, it doesn't choose one path. It takes both, creating an interference pattern on the detector. But if you try to spy which slit it went through, the pattern vanishes. Many worlds explains this neatly. The act of measurement entangles the particle with the observer, splitting reality into one universe where you saw it go left and another where it went right. The interference pattern, just parallel worlds overlapping before the split becomes irreversible. Here's where it gets cosmic. If quantum tunneling drives these splits, then the multiverse isn't a static collection of worlds. It's a living, breathing entity, endlessly proliferating. Every star, every galaxy, every conscious being is constantly forking into new versions. In one universe, a quantum fluctuation in a distant nebula tunnels into a new configuration, igniting a supernova that never happens here. In another, a neuron in your brain tunnels differently, altering a memory, a decision, a life. The sheer scale is incomprehensible. Every second, your body's trillion atoms undergo countless quantum events, each one a potential branch point. You're not just living in a multiverse, you're generating it moment by moment. Critics argue this is extravagant. Why invoke infinite universes when one suffices? But supporters counter that tunneling offers an elegant mechanism. The math doesn't favor one outcome over another. It simply allows all outcomes with branching as the natural consequence. No collapse, no observers magically shaping reality. Just the cold, relentless calculus of quantum probabilities playing out in full, and the eerie thing. This might solve one of quantum mechanics' oldest puzzles, why we only ever see definite outcomes. The answer: we don't. Every outcome happens, we just experience the branch where it went this way. The implications rewrite existence itself. Forgotten loves, lost chances, civilizations that rose or fell differently, they're not gone. They're real, thriving in branches you'll never see. Quantum tunneling isn't just a particle trick. It's the universe's way of trying every door, exploring every path, ensuring no possibility goes unmade. So the next time you hesitate at a crossroads, remember, somewhere you didn't, and both versions of you are certain they're the real one. Imagine the universe as a vast, shimmering hologram, where every star, every atom, even the void between galaxies isn't truly three-dimensional, but a projection of information encoded on a distant two-dimensional surface. Now take this one step further. What if that information wasn't just stored, but woven together by quantum entanglement, with tunneling acting as the loom that stitched the first threads of reality into existence? This is the holographic entanglement genesis theory, a vision so radical it suggests space and time didn't emerge from a singularity. They condensed from a quantum network of infinite connections, sewn together by the universe's first tunneling events. At its core, this idea marries two of physics' most mind-bending concepts, the holographic principle and quantum entanglement. The holographic principle, born from black hole thermodynamics, proposes that all the information in a volume of space can be encoded on its boundary, like a 3D movie projected from a 2D screen. Entanglement, meanwhile, links particles across vast distances so intimately that measuring one instantly affects its partner, as if they share a hidden language. Combine these and you get a universe where space-time isn't fundamental, it's emergent, a tapestry of quantum correlations that only appears continuous because the stitches are too fine to see. Quantum tunneling enters as the cosmic tailor. In the pre-Big Bang quantum foam, particles wouldn't have been isolated actors but nodes in a seething web of entanglement. Most connections would flicker in and out, but tunneling could have stabilized them, allowing entangled pairs to breach energy barriers and forge lasting bonds. Picture 1,000 fireflies blinking in chaos, then, suddenly, some sync up, their flashes lasting longer, spreading order through the swarm. That synchronization, driven by tunneling, might have been the universe's first coherent structure, a scaffold of entanglement that space-time later draped itself over. The math behind this is staggering. In this framework, every bit of space isn't empty but crammed with Planck-scale entanglement bonds, tiny wormholes, in a sense, linking every point to every other. These bonds wouldn't obey classical physics. They'd fluctuate probabilistically until tunneling events locked them into place, like a puzzle snapping together. The famous Einstein-Podolsky-Rosen paradox, where entangled particles seem to communicate faster than light, becomes geometry. Their connection isn't spooky action at a distance, but a microscopic wormhole, a tunnel through the quantum substrate. What's breathtaking is how this redefines the Big Bang. Instead of an explosion in space, it might have been a condensation of entanglement, a phase transition where the quantum web grew so dense, it crystallized into the dimensions we recognize. The energy released wouldn't have been fire, but the unlocking of correlations, like a frozen lake melting into flowing water. Even inflation, that mysterious faster-than-light expansion, could be reframed. Not space stretching, but entanglement spreading, weaving new spacetime into existence stitch by stitch. Evidence might already be hiding in plain sight. The cosmic microwave background, the afterglow of creation, shows subtle fluctuations that could mirror the universe's original entanglement patterns. Black holes, those entropy factories, might be knots where the fabric of entanglement frays, revealing the holographic threads beneath. And if spacetime is truly built from quantum links, future gravity wave detectors could spot anomalies, ripples that move too coherently, betraying the granularity of their quantum loom. The most profound implication: if entanglement and tunneling built reality, then the universe isn't just connected, it's inseparable. Every particle, every galaxy, every conscious thought might trace back to those first quantum stitches, a cosmic embroidery where the needle never stops moving. So next time you feel the ground beneath your feet or gaze at the stars, remember, you're not just standing in space, you're standing on it, a hologram woven from entanglement held together by tunneling's invisible hand. At the smallest scales imaginable, far beneath atoms, quarks, even the tiniest ripples of energy, space-time might not be the smooth, continuous fabric we perceive. Instead, it could resemble a frenzied quantum network, a seething web of nodes and connections flickering in and out of existence like static on an old television screen. This is the quantum gravity model, a radical reimagining of reality where the dimensions we take for granted, length, width, depth, even time, aren't fundamental. They're emergent, cobbled together from a primordial soup of quantum connections that abruptly crystallized into order through a tunneling event more transformative than any explosion. Picture the universe's infancy not as a dense, hot singularity, but as a formless void buzzing with abstract relationships, a cosmic game of connect the dots where the dots are the connections. In this state, concepts like here and there held no meaning, distance and direction were undefined. Then, as the cosmos cooled, this chaotic web faced a critical juncture, remained disordered or tunneled through an energy barrier into a stable geometric phase. Quantum mechanics, ever the rule breaker, chose the latter. The network froze, its connections locking into a rigid lattice, the first scaffolding of space-time itself. It's like watching liquid water suddenly snap into ice, except the ice isn't made of molecules but of crystallized quantum links. The brilliance of this model lies in how it sidesteps the singularity problem. Instead of an infinitely dense point where physics breaks down, the Big Bang becomes a phase transition, a moment when the quantum network structure shifted from randomness to order. Tunneling provided the escape route, allowing the system to bypass classical energy barriers and leap directly into a new geometry. Think of it as a cosmic defibrillator. The universe's chaotic heartbeat flatlined, and quantum mechanics delivered the shock that jump-started reality as we know it. What's truly dizzying is the implication. Space-time isn't the stage, it's the performance. The lattice of connections defining space could have taken countless other forms. Some configurations might have produced universes with 2 dimensions, others with 7 or more. Our 4-dimensional reality isn't special, it's just the roll of quantum dice that stuck. Even now, remnants of this primordial network might linger. If space-time emerged from a quantum graph, defects in its structure like cosmic strings or gravitational anomalies could be the fossilized scars of those first tunneling events. The echoes of this transition might still be detectable. If the early universe's quantum links froze unevenly, light traveling across the cosmos could carry subtle distortion stretches where space behaves slightly stiffer or softer than expected. Some theories even predict that black holes, those space-time warping anomalies, are places where the network melts back into chaos, temporary returns to the pre-geometric froth. But the most humbling thought, if quantum gravity is correct, the universe didn't create space and time. It discovered them, tunneling from noise into harmony like a radio tuning into a signal. And somewhere beyond our cosmic horizon, another network might have crystallized differently, a parallel reality built from entirely different rules, humming along in dimensions we can't fathom. So the next time you check the time or measure a distance, remember, you might not be observing the fabric of reality, but the shadow of a quantum gamble, a single tunneling event that spun chaos into order 14 billion years ago. One of the most perplexing puzzles in physics isn't about what the universe contains, but whether it remembers its own birth. At the heart of this mystery lies the information conservation paradox, the idea that quantum tunneling, while explaining how the universe could emerge from nothing, might also erase the very blueprint of its creation. Normally, the laws of physics treat information as sacred, every particle interaction. every force leaves an imprint that could theoretically be traced backward, like rewinding a film. But when you apply this to the universe's origins, the rules seem to shatter. If reality tunneled into existence from a quantum fluctuation, where did the instructions for that fluctuation come from? And more unsettling, could they have been lost forever in the process? This dilemma cuts to the core of quantum gravity. Black holes already forced physicists to confront information loss. Thanks to Hawking radiation, particles escaping a black hole appear to carry no trace of what fell in, violating quantum mechanics' insistence on reversibility. The universe's birth presents an even starker version of the problem. Imagine tossing a library into a bonfire, then trying to reconstruct every book from the ashes. Now replace the library with the initial conditions of the cosmos, and the bonfire with a quantum tunneling event so violent it scrambled the very concept of before. Where does that leave us? Some theories propose audacious solutions. The holographic principle suggests information isn't truly lost, it's smeared across the universe's boundary like a cosmic backup drive. In this view, tunneling didn't erase the universe's source code. It projected it onto a two-dimensional surface we can't perceive. Others, like loop quantum gravity, argue that spacetime's granular structure preserves information in the geometry of its quantum loops. Think of it as the universe encoding its own history in the wrinkles of its fabric. Even the multiverse offers a twist. If every possible quantum outcome plays out somewhere, then information isn't destroyed, just scattered across infinite branches. But the most radical idea comes from quantum Darwinism. The notion that the universe's constants themselves are a form of preserved information. If our cosmos is one of many in an evolutionary tree, its laws might be the genes passed down from parent universes via black hole singularities or brane collisions. Quantum tunneling, then, isn't a deletion, it's a transcription, copying select information into each new reality like a cosmic game of telephone, the fine-tuning we observe. Just the universe inheriting successful traits. Critics counter that these are elegant guesses, not answers. Without a theory of quantum gravity, we can't know if information truly survives tunneling, or if the paradox reveals a deeper flaw in our understanding. Yet clues might lurk in the universe's oldest light. Patterns in the cosmic microwave background could encode pre-tunneling fluctuations like shadows of a forgotten alphabet. Others hunt for anomalies in quantum entanglement, where particles might retain ghostly links to the pre-Big Bang void. What's at stake isn't just academic. If information isn't conserved, the universe has no memory, no way to retrace its steps. We'd be living in a cosmic amnesiac's dream where the past is irrecoverable. But if it's preserved, even through tunneling's chaos, then somewhere in the quantum foam, the universe's first whispers might still be waiting, etched into spacetime itself, waiting for us to decipher them. Frank Tipler's omega point theory isn't just a vision of how the universe ends, it's a prophecy of how it might cheat death itself through a quantum loophole. Picture the far, far future, trillions of years from now, when the cosmos has expanded so much that galaxies vanish over the horizon, stars burn out, and even black holes evaporate into a feeble haze of radiation. The universe, cold and empty, seems destined for oblivion. But Tipler, a maverick physicist with a flair for the audacious, proposes a twist. At the very brink of nothingness, quantum tunneling could trigger a resurrection, catapulting reality into a new existence through a final, cosmic singularity. This isn't science fiction, it's a radical reimagining of the universe's death and rebirth, where the laws of physics themselves become a ladder out of the abyss. Tipler's omega point hinges on a wild but mathematically rigorous idea. As the universe approaches its final state, the sheer density of information processing thoughts, computations, even the residual flickers of intelligence surviving in the void, could create conditions ripe for a quantum leap. Just as particles tunnel through barriers they shouldn't cross, the entire cosmos might tunnel through its own extinction, emerging on the other side as something entirely new. It's as if the universe, in its dying breath, whispers a quantum password to restart the system. How could this possibly work? Tipler's framework leans on the bizarre physics of closed time-like curves, hypothetical pathways where time loops back on itself. In the universe's final moments, as matter and energy are compressed toward infinite density, general relativity predicts that space-time could twist into knots, creating a singularity where the distinction between past, present, and future dissolves. Quantum tunneling, normally the domain of subatomic particles, could scale up to this ultimate singularity, allowing the universe to bypass its own end and cycle back into a new Big Bang. Imagine a snake swallowing its tail, except instead of a loop, it's a quantum teleportation, a discontinuity in the fabric of causality itself. The implications are staggering. If the omega point is real, then intelligence isn't just a fluke of cosmic evolution, it's a necessary ingredient for the universe's survival. Tipler argues that conscious observers, whether biological or artificial, act as cosmic archivists, their computations weaving the threads of reality into a coherent whole. In the end game, their collective processing could reach a critical density, warping spacetime enough to trigger the tunneling event. It's a dizzying thought. The universe might need us or our distant descendants to complete its own rebirth. But here's the kicker. This theory doesn't just rewrite the end of time, it erases the very concept of a finale. If quantum tunneling can resurrect the cosmos, then death and birth aren't in points but phases in an eternal cycle. Each iteration might tweak the laws of physics slightly, like a sculptor refining a masterpiece over infinite drafts. Critics, of course, dismiss this as speculative numerology, pointing out that Tipler's math relies on untested assumptions about dark energy and quantum gravity. Yet the core idea that tunneling could transcend entropy resonates with cutting-edge work on quantum information and black hole thermodynamics. So if Tipler is right, the night sky isn't just a graveyard of dead stars. It's a chrysalis, and somewhere in the far future, when time itself runs thin, the universe might just perform its greatest magic trick yet, disappearing into the void, only to tunnel back into being like a phoenix forged from quantum uncertainty. From the void of nothingness to the fire of creation, from infinite branching realities to black holes birthing new universes, these 30 theories reveal quantum tunneling as the universe's most audacious architect. It's not just a quirk of particles, it's the cosmic brushstroke painting galaxies onto the canvas of existence, the invisible hand rewriting the rules of reality itself. Whether tunneling birthed our universe from a random hiccup in the quantum foam, stitched it together from entangled threads of space-time, or set it adrift in an endless sea of bubble multiverses, one thing is clear: the line between impossible and inevitable is thinner than we ever imagined. What's truly breathtaking is how these ideas stretch physics to its breaking point, and then dare to go further. They turn black holes into cosmic wombs, entropy into an illusion, and the Big Bang into a single note in an infinite symphony. Some theories feel like poetry written in equations, others like fever dreams scrawled on the walls of reality. But each one, no matter how wild, forces us to confront the unsettling truth: the universe doesn't play by our rules. It cheats, it tunnels, and in doing so, it becomes something far stranger and more magnificent than we ever conceived. Now, we want to hear from you. Which of these theories hooked your imagination? The holographic universe, where we're all just shadows on a distant boundary. The Boltzmann brane nightmare, where your entire life might be a quantum mirage. Or the time crystal hypothesis, where the cosmos pulses like a metronome older than time itself. Drop your favorites in the comments. We're obsessed with these conversations, and your ideas might just spark the next deep dive. Because here's the thing, this isn't the end. It's barely the beginning. Every year, new discoveries rip open fresh mysteries in quantum cosmology. Are wormholes lurking in lab experiments? Will we ever detect echoes of a parent universe? And what happens when we finally crack the code of quantum gravity? One day, we might look back at these theories as quaint stepping stones or prophetic glimpses of a truth too vast to fathom. Until then, keep questioning, keep wondering, and remember, the universe didn't just happen. It tunneled, and somewhere out there, it's still tunneling, rewriting its own story with every quantum leap.